All right, what I hope is my last problem of the night, because this is your homework and not mine, is 9. Oh, I don't want to do green. Yikes. Let's go back to black. Okay, so 9.20. This is actually an interesting problem. You have one leg here, and you have some uniform mass here, and a very similar uniform mass, but instead of being the same size, it's half as big and half as massive. So I believe this is L here, and that makes this half L. All right, the question is, they give you the mass, and in my case it's 930 kilograms. They want to know what's the vertical support force at A. So if you look at A, there's going to be some, I'll draw it really long, some F at A and some F at B. And what they're going to, why they're there, why there's those supporting forces, is there's some Fg due to the mass here, and there's also some Fg due to the half mass there. Should probably obviously make this one way longer than, well, maybe not way longer, maybe twice as long as this one over here, but whatever. So some of the forces in the y direction have to be 0. It's balanced, right? So Fa plus Fb, the two upward forces, have to balance the two downward forces, which is 1/2 mg plus mg. Which is all well and good to say that Fa plus Fb equals, what's that, 1.5 mg or 3/2 mg. That's great, but we don't know what each of these are. So we could look at some of the forces in the x, but that doesn't seem very smart because there are no forces in the x, so it doesn't really help us. So we need a third tool, which is the sum of the torques about some point. I'm going to say, well, let's not call A, let's call it x. Has to be 0. In this problem, you want to know both forces. You want to know this one and this one. So I don't think it really matters which one you pick, but because you want to know Fa first, let's sum the torques about this point right here, x. And by the way, this mass doesn't hang over the end, but whatever. Even if it did, if it was uniform and it hung over each side equally, that would be great. But it doesn't, it's just a bad drawing. So if this is our point x here that we want to sum the torques about, Fb doesn't contribute a torque. There's no torque due to that one. Fg of the larger mass contributes a torque in that direction, because this would want to rotate that way. This Fg does the same thing. And this force down here, this reaction force or normal force or support force, whatever you want to call it, has a torque in that direction, which is a good thing because this one balances this one and this one. So if I write that out, I get Fa times, we need to know the distance from, the perpendicular distance from A to that point x. You always want to think about the line of action. There's the line of action of Fa. There's the perpendicular distance. That would be, whoops, times L. I didn't mean to zoom in. Minus, let's do the half mass. 1/2 mg times, how far away is that? Because it's uniform, it's halfway along this, which is half of L. So that would be times 1/4 L. Minus the bigger mass, which is mg, and it's located, its center of mass is right in the center, so its distance is 1/2 L. And they have to sum to be 0. So L's drop out of everything. And well, let's see, Fa is equal to, I got to do the math here, 1/2 times 1/4 is 1/8 mg plus 1/2 mg, which I believe is 5/8 mg. So you can do the math there and get that answer. Now, luckily, the easier part here is what's Fb? you can go back, substitute in right there, and you get what FB is equal to. Or if you wanted to make it a longer problem, you could sum the torques about some new position Y and choose Y to be over here. And then you could solve for what FB would be using the same approach here, using the sum of the torques. This is probably easier for the second part. Good luck.